Toda. Today we're going to talk about Bitcoin, not just not blockchain in general, but Bitcoin specifically. And so these slides are inspired by Aviv Zohar from Huji, from whom I stole some paintings, pictures. But he knows about it, so it's okay. So let's just start. We'll talk about what is Bitcoin, what is the blockchain, how does it work, and what can we do with that data science on Bitcoin and the blockchain, and also about some ways that we can like some Python packages and stuff that will help you if you want to start yourself. So what is Bitcoin? It's a decentralized digital currency. So we'll talk a little bit about what this means, but mainly there's no bank, there's no government, there's no one controlling the money. Unlike in shekels or in dollars, where the US bank controls the money, here nobody controls the money, nobody prints the money, no one can just print Bitcoins. Like no centralized government. And it was invented by Satoshi Nakamoto. It's in quotes because nobody knows who Satoshi Nakamoto is. There is a very poor Japanese guy whose life has been ruined by this. But he's not Satoshi Nakamoto. There's theories, but nobody still knows who he is. And it was launched in 2009. So Bitcoin promises to be pseudonymous, not anonymous. We'll talk about the difference between this. The transfers are irreversible. So if I paid someone money with Bitcoin and I didn't get my money's worth, I can't like call the bank or the credit company and complain that I didn't get the money is gone. There is a fixed amount of Bitcoins that can be mined. We'll talk about mining and what that is. And there's I think 26 million is the top amount you can get to. Bitcoins can't be seized by the government. We'll talk about this because there's been precedent that it can, but technologically it can't. And it can bypass regulation and censorship in certain countries. So how do money transactions work today? If I want to transfer $1 to someone else, or Red wants to transfer $1 to Blue, so Red says to the bank, transfer $1. The bank goes to the database or the books and checks if Red does have $1. If so, it changes the books and moves $1 from Red to Blue and says to Blue, now you have an extra dollar. Nobody sees this money, but the transfer is accepted because someone vouches for it. The bank vouches for it. So we all agree that Blue has $1 and Red has $1 less. So how do we do this with a digital, decentralized currency? We have no bank now, okay? So Red still wants to transfer 1 Bitcoin to Blue. So if this were a cash transaction, Blue would Red would give Blue 1 coin and nobody would have to know about this. But because it's a digital currency, so there's no bank, and Red transfers to Blue and nobody hears about it, so it's like it didn't happen. So we can't have that. But there is no bank. So what the solution in Bitcoin is that Red sends out the request to everyone in the network. Everyone, if we're all Bitcoin users, everybody sees this request. Everybody individually updates their books saying that Red now has $1 less or Bitcoin and Blue has 1 more Bitcoin, and everybody checks their books to see if this is possible, and if so, the transfer is approved, and now Blue has 1 more Bitcoin. So this is a problem, as you can see, because everybody has to keep the books. Everybody has to keep their own copy of the database and update it individually. It has to sync up. So this is a problem. The blockchain is this database. This is what everybody keeps. So if you are a Bitcoin user, you keep on your laptop or desktop or phone, you're supposed to keep the entire blockchain. Right now, it's around 300 gigabytes of data. So, and there's like millions of users, so you can understand the extent of this wasted storage. But so and what is the blockchain? The blockchain is basically a linked list, but it's a smart linked list. It's what's called a Merkle tree or a hash tree. So it's composed of blocks. Every 10 minutes, a block is created in the system, and all transactions that occurred within these 10 minutes will go into the new block. And every block is labeled with a cryptographic hash of the previous block, okay? So we can't just I can't create a new block and insert it anywhere in the middle because the cryptographic hash has to match. And this is created within the system, and the hash changes. The hash function, and it's kind of randomized, so you can't mess with it. Okay, so this is basically how it works. So now a new block is created, and all the new transactions will go here, and okay, and we'll talk about how this happens. So how is a block created in Bitcoin? Every Bitcoin user keeps a copy of the blockchain and also runs the code, the core code. Okay, what this does is basically tries to solve a cryptographic puzzle, which differs in difficulty as time goes on, the difficulty increases. And if you're lucky enough to solve this puzzle, then you get a new block. This is what's called mining. So you get a new block and you mine Bitcoins. Today, if you get a new block and you mine a new Bitcoins, you get 25 Bitcoins for this. And you are now the creator of the block, and you've seen all the transactions that everybody's tried to send over in the last 10 minutes. You pick the ones that pay you the highest fee, and you insert them into your block, and you send it out to everybody, and everybody puts this new block at the end of their chain. Okay. So this is how it works. And this cryptographic puzzle, you basically can think about it as having to guess a very, very long binary string. So this is a hard problem, and you can vary the difficulty as time goes. And of course, this is completely run by the code. You don't know what you guessed or what is the answer. So this is how it works. And at current rate, the difficulty is that set at approximately every 10 minutes, there's a new block created. And this is, of course, in expectation, not exactly 10 minutes. So what is a Bitcoin transaction? If a transaction in Bitcoin are a little more complicated than regular transactions, because if I have 10 Bitcoins, I want to send to someone 1 Bitcoin, I have to send all of my Bitcoins and split them into 2. 1 I will send to whoever I want to transfer money to, and 9 I will transfer back to myself, maybe to a different account of mine. But I have to send everything out. So there's multiple inputs and multiple outputs possible for every transaction, which is important because we'll talk about it in the data science aspect of Bitcoin. So this is what the blockchain looks like parsed. I ran some code to parse it. And so you see, this is a block. This is the first block in the blockchain, the ever. Okay, so the previous hash is 0. And this is the Merkle root, it doesn't matter. And this is a new transaction. We can see there's inputs and outputs. This is the input. So this is a very basic transaction because there were no Bitcoin users at that point in time. But we'll see, this is a transaction from 3 years ago, approximately. And now we have multiple inputs in the same transaction. I think there were 100 inputs for this transaction and 1 output. Okay, so this is someone that was doing something a little bit fishy, right? Moving money around, a million inputs into one transaction. This is not a regular transaction, but this happens a lot in the blockchain. So okay, so whenever a block is created, someone collects you pay a fee for your transaction, and the transactions are adopted according to highest fee. And there's, okay, we can talk a little bit about what happens if 2 blocks are created simultaneously. Because this is a problem, right? What if I have a lot of computational power and I disconnect my computers from the internet and I start mining and mining and mining, I run my code and I get a new block. And now I want to double spend my money, which means basically I want to spend 1 Bitcoin and make it into 2 Bitcoins. So what can I do? I can create a transaction in my block that I send all of my money to myself. And then I can tell someone else that I sent him my Bitcoin. Okay, I can I can tell him, okay, look at this transaction, I'm transferring my Bitcoin to you, and then immediately after he sends his goods in return for my money, I propagate my already mined block. So now my block competes with this innocent block, and maybe I can I cannot pay for my goods if my block takes. So in order for this not to happen, the protocol works according to a longest chain rule, which means that if I sent my block out and already 2 or 3 blocks were created in the other chain that everybody else sees, then the longer chain wins. And there is the promise that Satoshi wrote in his paper that if no one controls more than 50% of Bitcoin, the Bitcoin computational power, then this can't happen. Exponentially, the chance of you doing this exponentially decays in time if you don't control 50% of the network. This is false. Okay, this was disproved, and there are examples of people. If you control around 34% of the network, you can do things like this, and this has happened in the past. Okay, if you propagated your block and it was adopted by everyone, and nobody still has a longest chain, then you win. So you have to you play on the variance of this. If you have a lot of computational power, you control the variance more than small players. This is what's called the selfish mine attack. Okay, so if you really want to know that your transfer is confirmed, you really got Bitcoins for your goods, you better wait a few blocks until this happens. Because the longer you wait, the more chances are, the lower the chances someone can steal your money. But a block is created every 10 minutes, so this means you maybe have to wait half an hour to confirm your transaction, which is a lot of time. So this is not really feasible in real life transactions that we do, and the truth is nobody really uses Bitcoins for real transactions today. It's not effective as money today. Okay. So this talked about a little bit. So it's true that the more mining power you have, the more chances you have of mining block, and the bigger your mining pool is, you control the variance more. Because if you're a small player, it's true that in expectation you have to wait the same amount of time, but it's not true. Like the variance is very high. So being in a part of a large pool enables you to do more. Okay, so this is how the mining pools are split. This is I took this from Blockchain Info like a month ago. So you can see the largest pool is 16%. In 2014, there was a pool that controlled a little over 30%. So 34, it can happen if like these three combine. So this is mining pools. Now we'll talk a little bit about Bitcoin anonymity. So the way Bitcoin works is that everybody has a public key and a private key. And transactions, as you see them in the blockchain, you can only see the public key. Right? You saw when we looked at the parsed blockchain, you saw this like hashes and public keys, and you didn't see names or IDs. So basically, nobody knows how to connect your public key to your private key except you and your wallet specifically that you work. So this is very nice, like for if you want to, I don't know, buy and sell drugs or children or I don't know, weapons or whatever people do with Bitcoin. No, nobody goes to the grocery store to buy with Bitcoin. Okay, so and you can generate as many addresses as you want, so you can have as many public keys as you want, and it becomes increasingly hard to trace after a while. But you can do it. So you can actually. Oh, and there's of course people use additional anonymity services like Tor. And but the bottom line is that everybody can see every transaction. You can't maybe know who it is that made this transaction, but you know you know about every transaction since the beginning of time with Bitcoin. So this is like a gold mine for data scientists, right? Okay. So what can we do? Okay, so in 2013, I think, Adi Shamir and Dorit Ron from Weizmann Institute had a very nice idea. I think it's like a nobody thought of it at the time, but it's not a very out there idea. They said, create a graph of Bitcoin transactions, parse the blockchain into a graph of transactions, then group together transactions with multiple inputs using union find or something like this, which is, it makes sense. Like if two people are transferring money to the same transaction, you can usually assume that there's the same entity. And this is, you produce something called the entity graph, and you can also use clustering methods to see, because it's unlikely like that the drug dealers and the, I don't know, pornographers talk to each other that much. So you can see a cluster of each kind of criminal, I think, in Bitcoin pretty easily. And also, you know, a lot of information, because some people advertise, like money launderers advertise themselves. And of course, exchanges, you can know who they are. So you can eliminate a lot of noise and do a lot with this. And this is actually something that Shamir and Ron already did in 2014. So they created this entity graph. It was a lot smaller at the time. Now it's harder to do because it's just computationally harder. But it's not that hard. Like we managed to do this with, I think, 500 gigaram, which this is a very good use of university resources. So we'll see a positive and negative example of this. So a positive one is actually when the FBI used these methods to dismantle the Silk Road, the original Silk Road. If nobody, okay, so the Silk Road, if you've ever gone into the dark web or looked around like I did in 2010, I think, you immediately get to the Silk Road, which is basically eBay for criminals. You can buy drugs, you can buy weapons, you can buy anything you want. And of course, using Bitcoin, so nobody can ever find out. And there was a guy controlling, the guy that founded the Silk Road called himself Dread Pirate Roberts. Which is funny, I think. And and the FBI had enough of this, so they were like, we're going to find this guy. So they spent a lot of resources, and they used methods that Shamir and Ron suggested, and they got to some, they didn't find the guy, but they found a lot of people that were possible targets, and then they did a lot of good old-fashioned intelligence. And they found the guy. His name is Ross Ulbricht. He was 25 years old. He was living in a roommate apartment, even though he had 700,000 Bitcoins. And they decided they were going to take his money no matter what. Because, okay, so remember, you can't seize Bitcoins. You need the private key. And they knew this guy would never give them the private key if they catch him. So they had to actually catch him in the act of transferring Bitcoins, using this account linked to Dread Pirate Roberts. So what they did is they ambushed him in the library where he worked. They went in and waited until he opened his laptop and inserted his password to his account, and then they jumped on him and took his laptop and transferred the Bitcoins. So this is kind of low-tech, but still impressive. So it's a way to do it. So they can be seized. Okay, so this is the Silk Road. You can see you can buy MDMA and Valium and weed, whatever you want. Okay, and this is the transaction graph that they created, and they seized the Silk Road and they seized the Bitcoins and they put it on the account. They were like, we seized these Bitcoins. They managed to get 144,000 out of, I think, 700,000 or something like that. So not everything. He wasn't that stupid. So, okay, they were for sale. I don't know if you saw this. You could buy them at the time. I think you still can buy some of them. A lot of Bitcoins. So probably the US government made a lot of money from Bitcoin. But there's also a negative example of when this didn't work, is when Shamir and Ron themselves tried to find Satoshi Nakamoto, and they found an unrelated guy, a security researcher guy. No, this is Ross Ulbricht. And this was very embarrassing because they raided his office and he wasn't the guy. Okay, so sorry. So what was the problem with their method? So the basic idea that they had is that multiple inputs are the same entity, but there are actually mixing services. People who supply services that exactly for this purpose, like just transfer your money into and out of a lot of accounts, just to make it harder to track. I'll show you an example of this. And also it becomes computationally hard as the graph grows because there's like millions and millions of nodes now. It's not that easy. Even if you have a linear or a time algorithm for it, it's harder. Okay, so this would be a normal transaction, or this also is a normal transaction. You see money going in and out, like nothing suspicious about it. But then you have this mixed transaction. So and now each one of these, if you open up, it's another million transactions. So it's kind of hard to track. So okay, so that was the data science part. Any questions about it?
So they use one address for every transaction, but how can they really do that? It's like what service they use that gives them that?
You can just it's built into the protocol. You can have as many addresses as you want.
Just the but what about the IP addresses you use to?
It doesn't matter. You don't need an IP address. You just need your private key, and you can open as many addresses, public keys as you want.
For what you're saying, basically you can do a denial of service, but you can flood the entire network.
This happens today. Yeah. You can
purposefully flood the entire network and blow up artists.
What happens today is it's not. Today, what happens is because there are far more transactions, because people are buying bitcoins for investments now. So there are a lot more transactions than the block size is 1 megabyte. There's one every 10 minutes, so there's a lot more transactions than what can fit in a block. So what happens is actually transactions with very high fees get in. So you again can do a little double spending attacks. Like you can transfer money to yourself with high interest and money to someone else with very low interest and low fee. And
but every transaction costs a fee.
Yes. So a little bit about Python. There's not much to tell really. It's very simple to start exploring. Once you find a normal package, there's a few packages, but I use the blockchain package. And Block Explorer specifically, it's very easy to use. You have to notice a few things if you look at an output of a transaction, it's actually the public key, but the input of a transaction is not the public key, but a pointer to the previous location, to the previous block and transaction in which this person was an output public key. So it's a little messy, but you can it's not hard to do. And I also use NetworkX, but don't use it if you're going to do large projects on Python because it doesn't hold up for large numbers. Use a local database if you're going to do a thing on the entire blockchain. Okay, so and this is an example of code. You'll have it in the presentation on the website, I think. But so basically, what you see here is I created this entity graph. I used Union Find which I didn't show here, but it's very simple to write. And I merged together everything that is multiple inputs and created an entity graph. And you see it's a very short code, even though it does something kind of sophisticated. So it's very easy to use. So the package you want to use is a blockchain package, which is natural if you want to do things on blockchain. But it took me a while to find. So, okay. Any questions about this? Yeah.
What are the practical limitations of networks?
I couldn't find theoretical specs, but I saw that if you get to 1 million nodes, you're in trouble.
Where from do you download the blockchain?
Look on the internet on how to download the blockchain.
You need to download all of it, or you can
no. What you do is you install a wallet, and then you become part of the wallet comes built in with all the source code you need to run, and you run it, and it downloads the blockchain to your computer, and you have a wallet and a private key and a public key.
How much is the entire blockchain?
Excuse me?
How much is it, the entire blockchain?
Right now, it's something around 250, 300 gigabytes.
So if you run a wallet on your phone,
Okay, so this is a good question. Now there are services that allow you to keep only part of the blockchain, like the last few blocks on your phone. But this is a problem, okay? Because we talked a little bit about what you can do if you have a lot of computational power. So if not everybody keeps the blockchain on their device, this increases the power of mining pools in the network. So every user that doesn't keep all of the blockchain on their local device is actually harming the stability of the network. So these services are not so good for Bitcoin. Also, one thing that I wanted to add, mining is very, very expensive in electricity, and around 0.1% of the entire world electricity take-up is Bitcoin mining. This is more than like 100 countries. This is insane amount of electricity. So yeah, and it's growing. Yeah.
So now there are more coins than just Bitcoin, and I'm wondering if you've been in terms of research other to see if there is something new that maybe overcome some of the difficulties that you raised.
There's a lot of different protocols, a lot of different currencies, and they address different things. Like, so you have Ethereum that lets you do smarter things in terms of contracts, and the block size is bigger, and there's more blocks per time period. But this doesn't really solve it. There's a lot of protocols, like there's the Spectre protocol, and they're doing DAG instead of list. So, but it's not the technology is not there yet in terms of the blockchain. One more question?
Something about Ripple being like exactly the opposite of the original idea. It serves banks and...
Okay, yeah, so a lot of banks and countries are working on this also. So Ripple is not doing something very original in this sense. The Bank of England is working on its own cryptocurrency. But the thing is that Bitcoin, like, this is why criminals like it, it's not regulated. So anything that is like moderately regulated is like, it's a different thing. It's a good thing, I think, but it's a different thing than what Bitcoin offers.
After you saw all of that, what do you think personally of blockchain and all the hype around it?
I think it's a very, very interesting philosophical question. Like it's very interesting. It's like the internet, basically. It's something that completely bypasses regulation. It takes away money from the government, which is like the main power of the government is money. So this is like, it's a revolutionary thing in terms of concept, but the technology is not there. Okay, so thanks.